Okay, I'm pretty excited about today. Of course, I'm always excited. Every new piece of material, I'm like, oh, vibrational spectroscopy, it's my favorite. Well, molecular orbital theory is my favorite also. So I have favorites in every lecture. So today we're going to do the introductory lecture on molecular orbital theory and start making MO diagrams. Last time we talked about some of the shortcomings of local bond theory and how it was great for what? What was the scope of local bond theory? It was big, but there's a couple of exceptions. Yeah, so what was it good for? Structures is the word I was looking for. Yeah, so building molecules and structures. It was really good for structures. And in fact, we still kind of use it. We still do use it as initial guesses for Gaussian. So we'll use our local bond theory knowledge and VSEPR shapes to build our molecules as an initial guess. And then we'll put those in and let Gaussian calculate the electronic structure. So the molecular structure is where all the atoms are located. But the electronic structure is where local bond theory fails. The electronic structure is the structure of the electron cloud. The most complex thing about the molecule is that oscillating electron cloud. And so that's where local bond theory fails, because local bond theory says there's two electrons between each atom, and that's the bond. But think about it, it's not that simple. Okay, those electrons are oscillating all over the molecule, and that's why we have molecular orbital theory, and that's what we're starting today. Just want to make sure. Okay. So we've talked about local bond theory. Today we're going to start with the introductory parts of molecular orbital theory. So we're going to focus on the simplest molecules at first, homonuclear diatomics. So same nucleus on each end. So N2, O2, C2, B2, Li2, all of the same kind of atoms on both ends. And all homonuclear diatomics are D infinity H. So we have one character table, one point group to deal with. Now, this was also these were also the first molecules that they studied in science. And so they started out with the Millikan notations in Greek characters, but it got cumbersome. Okay, so then they have switched all of the characters over to A's and B's and C's, so English. And so I've gone ahead and done that for you, even though if you look up a character table and it's D infinity H, you're going to see sigma and pi and delta and so on, and pluses and G's and U's. These correspond to A1s, A2s, E1, E2, and then G's and U's. And what does G stand for? Gerade, very good. That's German for even. Yeah, and U is ungerade, which is uneven. Yeah, so even and odd, that's the G and U. Since this molecule is the same on both ends, it has an inversion center, and that's what the G and U tells you. So just to review, under I, the G's are all positive, and under U, the I character is negative. So they're negative under inversion. Okay, so you can have orbitals that if you invert them, the pluses and the minuses swap places. Okay. And so let's just make our simplest molecule. Remember that the colors that we draw are the oscillations, and they flash. So are they flashing together or out of sync? And that's the question that we have when we bring two hydrogen atoms together to make H2. Those 1s orbitals can be in phase with each other. So these down here are in phase with each other or out of phase. And so that's the question. And if they're in phase with each other, think about it. Now, again, this is a single orbital. So look how much the box has increased. The box size has gotten bigger, so the energy is lower. So from a hydrogen atom over here on the right, this is the box length, if you will. Now it has at least twice the space for that electron to move around in, so that drops. But then what about the upper one? The box length is big, but the curvature is increased because it has a node. So it's higher in energy. So we have the same kind of thinking that we have for the particle in a box applies even in these three-dimensional cases. You can think about how much room the electron has. That would definitely lower its energy. But then if it has lots of nodes, then it's going to make it go higher in energy. So you can start at the bottom of the molecular orbital diagram and just see that the nodes increase as you go higher and higher and higher. And so this would be, what happened? Okay, this would be the wave function, a way to write that wave function, we would call this a sigma bond. The sigma bonds they have rotational symmetry. So I could rotate that sigma bond and it would be the same. I really couldn't tell that I was rotating it. Even at the top, top one is a sigma bond as well. And this is the combination of 1sa plus 1sb. So pay very careful attention to these signs right here.
Is that where the even and odd come from?
Well, not really. It's where the different colors come from. So look at those signs and compare that to the colors of the orbitals. So this is a positive 1sa and a positive 1sb. So 1s is just saying the 1s orbital on atom A and the 1s orbital on atom B, and they're both positive. So the plus 1 implied up front here. So plus 1 and plus 1, so those are the same color. So that would be the bonding orbital. And then up here, they're opposite sign, and so they would be different colors. So those colors correspond to these pluses and minuses in the wave function. Notice how this, even though this looks, mathematical, it's really just the same as the pictures. So I'd like for you to get familiar with writing out these molecular orbitals using this kind of notation because it's very simple. This doesn't require a picture. But when you see this equation, you should see the picture in your mind. You should say, okay, 1s, A, and B, they're the same color because they're the same sign. Makes sense? Okay. It will get a little bit more complicated when we get to the p orbitals, but we need to make sure this makes sense first. Questions or responses or reactions? Okay. So each atom comes in with 1 electron each, and so then when we bond these together, those electrons are going to go to the lowest energy state that they can, so they're both going to end up in the ground state, in that lowest energy state. And so now we have a molecule with 2 electrons in that molecular orbital, and we have a single bond. Because it still does take 2 electrons to make a bond, but it's over the whole molecule, not just crammed between the 2 nuclei. Okay. What if we made H2 minus 1? So we would add another electron, and it would just go up here. It would go in that antibonding orbital. And it would weaken the bond because now the molecule has 2 electrons in the bonding orbital and 1 electron in an antibonding orbital. And it would have sort of half a bond. So you can think of this as bond order, which we'll calculate later. That you calculate all the bonding electrons and you subtract all the antibonding electrons and divide by 2 because you need 2 electrons per bond. And it will tell you how many bonds you have in this molecule. What if we had H2 minus 2? So we tried to put 2 electrons onto the H2 molecule. Then we'd have a bond order of 0 and it would dissociate. It would go to 2 negative hydrogen atoms. So it'd be 2 hydrogen atoms with 2 electrons in the 1s orbital. And so we'd have a minus H and a minus H repel each other and go off into space. And so then this energy difference between these two is dependent upon structure. So if we bring these 2 elements together, if they're at infinite distance, there's 0 energy difference between the bonding and antibonding. But as they get closer and closer together, you'll have a minimum in the bonding orbital, and that will be the equilibrium bond length for the molecule. And the antibonding will go up in energy, and this gap between those two is what's shown here in the MO diagram. So think about that too. As the molecule oscillates like this, then these energy levels also oscillate. Okay? So as they go further apart, the energy levels get closer together. And as they get closer together, the energy levels get farther apart. But if they get too close together, then the energy levels get really far apart. And so there's this oscillation between the energy levels as the molecules, as the atoms come together and go apart. Now that's also what smears out the lines in electronic spectroscopy. Because as you have vibrational motion, you have a bunch of different energy levels. And so in the UV visible spectrum, the peaks are really broad. Because underneath those broad peaks, you have all of these different vibrational excitations. And so you have, a mole of molecules, you have 10 to the 23rd different energy levels. They're all very close together, but they're smeared out over that whole vibrational manifold. So that's what's going on with this energy spacing. And then we can label these according to that character table. This bottom one is A1G, and this top one is A1U. Can you see that this is Gerada? The center of mass is right here, and so if you were to invert any part of that electron cloud, it would go through the center of mass and be the same color on the other side. And up here it'd be opposite color. So if I pick this spot right here and invert it through the center of mass, I end up over here, and it's a different color. It's the other color. So there would be a change in sign. So that would be a -1 under inversion, which would make it Ungerada. So you cannot connect, and everybody wake up on this statement, you cannot connect Gerada and Ungerada with bonding or antibonding. Okay? They're not connected. Sometimes Gerada is bonding, and sometimes Gerada is antibonding. So don't make that connection. Okay? Because in the pi bonding, it's different than this. So Gerada and Ungerada do not tell you whether it's bonding or antibonding. Okay? That's a false assumption that can be gathered from this chart, and I just want to make sure you don't latch onto that and put that in your head. Yes?
So how are these energies calculated? Like just using that equation? Because would that treat it as one electron, or like?
There would be one of these for each electron, and then you have, it gets really complicated. Then you also have to exchange those electrons and recalculate the energy. So you have, it's a matrix calculation of 2 electrons and 2 orbitals. And so you have all 4 possibilities that you have to calculate for every one of these orbitals.
So it treats them totally separately and then puts them together? Or like
Then the electron correlation term is where you really get into trouble. You can neglect it for Hartree-Fock theory, and then you can use perturbation theory to kind of correct for that. So that's where you really have to dig into what's going on in Gaussian. Dr. Arnie's trying to teach some of that in integrated. And so in integrated, you'll actually calculate the energies for some of these molecules. Okay, he'll do. I think he has you do H2 plus. That's as complicated as it gets. You still have 1 electron. Yeah. So, and then I think he might have you do either helium. I think you do helium atom. There you have 2 electrons. Yeah. So now let's look at p orbitals coming together. Now there's 2 ways p orbitals can come together, end on or side to side. And so think of these orbitals, these the frontier edge of these orbitals, think of them more as water drops, right? How water drops could come together, and then as soon as they get close, they merge. And so the shape changes when they touch. And so that's kind of what's going on. These orbitals come together. If in this case, you have this p and minus that p. I say this one minus that one because notice how they've flipped the sense. So this one has a darker orange on the right, and this one has a lighter orange on the right. And so as they come together, the darker pieces are in the middle, and they merge. Okay. Now remember what these different colors represent, or plus or minus represent. That's the expanding part of the orbital and the contracting part of the orbital. So they're expanding in the middle and contracting in the middle. And so when they expand, they splash together, and when they contract, they get small together, and then the outsides expand. And so this is going to naturally, they're going to smash together and merge in the middle and create this bonding orbital.
So it wouldn't be the expanding side and the contracting side meeting?
No, if that happens, then it's antibonding. We'll see an example of that. So this would be orbitals in phase where the overlap is favorable. So these overlap with each other, and we call that favorable overlap, which is what we need for a bond. Okay. And so this would be an antibonding one. I don't like the way they've drawn it because these are actually touching, but there should be more space between those two. So I should criticize Atkins for doing that. And so that can be so bold. So that has a node in the middle, and so that would be antibonding. So this is expanding, but at the same time, this is contracting. And so it's almost like that part of the electron cloud is running away from the expanding part. And then when this one gets big, this one shrinks. And so they never really overlap. Okay, it's not that the different pluses and minuses repel each other. That's not the case. It's just they just don't overlap because one's expanding while the other's contracting. And so they're just never there at the same time. And so it's when they're expanding together that there's a lot of overlap. And then they splash away, and then they expand together and splash away. And that's a bonding arrangement. So So the bottom one is a bonding arrangement. This one is an anti-bonding arrangement. I guess they do repel each other some, but because that's where you get the anti-bonding nature. But as far as the node, it's right there in the center. And so we would call these orbitals out of phase. And so there's a picture from Gaussian of the bonding orbital. And notice how there's still that rotational symmetry. I could spin this orbital around the bond axis, and it would be the same. You know, I have a C infinity axis along that bond. And so that's going to be a sigma bond. So sigma bonds have that rotational symmetry around the bond. So that's how you tell if it's a sigma bond. If there's rotational symmetry, or if it's the same around that bond, that would be a sigma bond. And so this would be a sigma bond here, and then this one above it would be a sigma star. So we put a star by the anti-bonding orbitals. So sigma and sigma star. Hopefully this is some review from organic. We've talked about these kinds of arrangements for years. Now let's talk about Gurata and Ungurata. Okay. So this one on the left is anti-bonding, but it's Gurata. And on the hydrogen one, the bonding was Gurata. So see what I'm saying? And you can't connect to the Gurata and bonding or Gurata and anti-bonding. You just have to look at the orbital and know. And so in this case, if I take this point here and I invert it, so I go through the center of mass to the other side, it's the same sign. And so that's why I get a G. And over here, if I take that point and go to the same side, go to the opposite side of the molecule through the center of mass, it's this different sign, and so that's Ungurata.
And because the right one is bonding,
because these are the same right here. So these are both plus and minus, and these will oscillate into each other. Yeah. Whereas this one over here, this has a node in the middle. So it has a node here. And this one does not have a node that cuts the bond, but both of these have this planar node here. I can't draw it very well with this pad here. Okay. And this one has a planar node. So both of the pi bonding arrangements have nodes that are planar nodes, and the bonding or antibonding happens above and below that plane. Notice this node breaks the bond right here, and that's really how we tell if it's antibonding. So if the node breaks the bond, it's antibonding. So you can write that down. If the node breaks the bond, it's antibonding. And that works in benzene and DNA and everything else. I mean, if you're looking at a molecular orbital and you're interested in a particular bond, does that molecular orbital have a node that breaks that bond? If it does, then it's antibonding for that particular bond. It might be bonding elsewhere in the molecule, but it might be antibonding for this piece. Like if you're thinking about, say, a dehydration reaction or condensation reaction where you're going to have to pull an OH off a molecule, and you wanted to know which molecular orbitals would help that along, you would look for molecular orbitals that had a node between that OH and the molecule that were going to break that carbon-oxygen bond so that it's weaker from that molecular orbital. If you could excite that molecular orbital, then you'd weaken that carbon-oxygen bond, and you could lose that OH. So here now we have the p orbital on A minus the p orbital on B. So remember this negative sign, what is that indicating? It indicates that the pluses and minuses are switched. Okay. So in that case, the pi star is 2p, the 2p orbital on A minus the 2p orbital on B. So does everybody see the connection between the picture and the little notation? Okay. And this would be 2pa plus 2pb, so the pluses and minuses line up with each other. And so that would be, again, the picture, compare that to this. The both plus sign here on both of those. So they're in phase, if you will. And then here's the Gaussian picture of one of the bonds, the pi bond in nitrogen. So there's a nodal plane, and then this is a bonding arrangement, so that would be a pi bond.
And that'd be the Ungurata.
That one would be Ungurata because if you go through the center mass, the green turns to red, and vice versa. So here's all three bonds in the 2p interactions for nitrogen. You have the end-on interaction from the 2p z orbitals. Now, how do I know it's the z? Well, the z-axis of the molecule is that rotation axis. So that's the principal axis of symmetry. That's going to be the z-axis. And so it's the 2p z orbitals that hit end-on and make the sigma bond. And it's the 2p x and y that go side to side. And here's the Gaussian pictures of it. You can't really see the left because it's too dark. It's great on my screen, so I lightened everything up because the projectors don't like the dark images. And you can see inside, you got the two nitrogens here. Here's a nitrogen and a nitrogen. So you've got quite a ball of electrons holding those two nuclei together. And the two s orbitals aren't shown, but the two s orbitals are in phase and out of phase on this as well. It's also incredibly symmetric, which means it's incredibly inert. I mean, that's why nitrogen gas is so non-reactive. It's so stable. It's got a triple bond. It's got a very symmetric electron cloud. So things that are trying to attack this molecule, there's really no handle, okay? Whereas oxygen is a diradical. It's a triplet state. And so it's got two unpaired electrons. So O2 is much more reactive than N2. So let's look at helium. So dihelium. We'll bring two helium atoms together, in phase, out of phase. We have 4 electrons total, 2 in the bonding, 2 in the antibonding. So we don't have a lot of helium-2 running around. Okay? So in fact, for all the noble gases, all the antibonding orbitals are full. And so that's why the noble gases are single or monatomic. Okay. So now let's look at fluorine. So we're putting together the two s orbitals as they come together in phase and out of phase. And we're putting together the pz's in phase and out of phase, and the px's and py in phase and out of phase. So we have all those possibilities. So this is a molecular orbital diagram. So that's, whenever we talk about an MO diagram, this is what we're talking about. So if I asked you to draw the molecular orbital diagram for fluorine, this is what you would draw. You wouldn't necessarily have to draw all the pictures. You'd have to draw what's on the left. Okay. So you come in with the two s orbitals at the bottom. Since it's a homonuclear diatomic, the two s orbitals for both atoms are the same, and they mix in bonding and antibonding arrangements, high and low. And then the 3p orbitals come in at the same energy, and then you mix those in pairs. So you have the pz's bonding and antibonding, and then the px and py bonding and antibonding, and those are doubly degenerate because it doesn't matter if you're in the x direction or the y direction in the symmetric molecule. Okay. So let's walk through this a little bit at a time. So we have the A1G orbital, which is 2sa plus 2sb, and the A1U, which is 2sa minus 2sb, and those are the pictures that correspond to them. Then we have this A1G, which is 2pz plus 2. I thought I'd change that. I actually think that should be negative. So let me go ahead and make that change. So I'm going to get in here and make this one a negative sign. And I'll tell you why. And this one's okay plus. I changed the top one but not the bottom one. Okay. Okay, so we get to this one, and I have the negative sign in there. Why do I have 2pz on atom A minus 2pz on atom B, and I call that a bonding arrangement? Think about how the z orbitals, those pz orbitals are on the z-axis, right? I've got the 2pz on atom A, and it's over here. Let me do this on the screen here. This one, if we call this atom A and this atom B, do you see how atom B has swapped sign compared to atom A? But yet when they come together, we have this nice bonding piece in the middle. And so this is bonding because of the way the orbitals come together. Okay. And so in this case, for the 2pz's, it's this minus arrangement that causes the bonding situation. And it's the plus arrangement up here at the top that causes the antibonding arrangement. See, 2pz on atom A and on atom B up here, we have this node now in the middle. Yeah, and so that's antibonding. So those are all of the sigma bonds. So the two s orbitals in phase and out of phase, and the two p z orbitals in phase and out of phase. Okay. Is everybody comfortable with that? Okay. And then we have the E1U, which are the 2px and y. I've only shown the notation for the 2px because it's getting too busy, but the 2py is the same. So I have 2px. I think that's where I must have changed this wrong sign earlier. So sorry, I'd made these changes this morning and I just picked the wrong orbital to change to a plus. Okay. All right, so this is the 2px plus on atom A and B. So here's atom A and here's atom B. And I have 2px on A and 2px on B, and they're the same sign, and so that means that we have this arrangement of the top and bottom. And then I have the next one, 2px on atom E minus 2px on atom B, and now we have that node here. And so that would be a pi star orbital. And you can see if this is the x direction, then you rotate it 90 degrees, and that's the y direction. You have the same kind of arrangements. And there's no difference in x and y energetically. If you don't have any external fields, you don't have any magnets or other molecules, we're calculating this molecule by itself in space. And so there's no change in energy from x or y. And so that's why we have degenerate orbitals, and that's why these are meant to be the same energy, and we have 2 electrons in each of those orbitals. So we can add up our electrons. We have 2, 4, 6, 8 in bonding arrangements. But we have 2, 4, 6 in antibonding. And so the net is 2. And you divide that by 2, you have 1 bond. So fluorine, this is predicting that fluorine would have a bond order of 1. And we call that a single bond. Here's oxygen. Looks very similar, doesn't it? You come in with the s orbitals and the p orbitals, you make the same shape essentially. And so then we have 12 electrons for oxygen, 6 from each. You put those in, and then you have only 2 electrons in this antibonding orbital here, which means it has an extra bond. So a bond order of 2. And the same ordering and designation from the Millikan symmetries. So let's look now at nitrogen. This is a little different. First of all, look at the pictures. What do you notice?
Curves.
Yeah, it's quite a bit different. So what's happening here? Why do I have this funny business going on down here? Remember when we were talking about symmetries in the character tables, that orbitals that have the same symmetry designation, like A1 or E, if they have A1, they have the same symmetry and they can all mix together. Okay? So A1 and an E can't really mix, but A1s can mix with all the other A1s. And for smaller atoms like nitrogen, carbon, boron, lithium, and what else do we have? Beryllium. Those s orbitals and p orbitals are pretty close together, and so they can have sp mixing. And so that's what's going on. Lithium through nitrogen feature this thing called sp mixing. And so this is just a complication in nature. We don't have necessarily a good theory for it. It's just what we observe. Okay. And so this lithium through nitrogen feature sp mixing. And so that's what's going on here. We have a little bit of p character mixed in with our s orbitals. And up here we have what we would call a little bigger p orbitals than we would expect, and that's the s mixing up here with the p's. So we have a little bit of s character mixed in with the p orbitals, and a little bit of p character mixed in with the s orbitals. It's greatly exaggerated in these pictures. But those are our sigma bonding arrangements. And so, again, the same symmetries that we've seen before. And then we have really no change on the pi bonding. And those are the symmetries that we have for the pi bonding. Yes?
Why is your 3 sigma higher than your
1 pi.
Because of this sp mixing. That's what's causing that to flip. And so that's why we have to cover this, because it changes the experimental data that we would predict from MO theory. So our MO theory was not matching boron or carbon, or it would match nitrogen either way, but it wouldn't match the nitrogen anions or cations. So when we take an electron out of this, or 2 electrons out of this, if we had it the other way and we took 2 electrons and we made dinitrogen dication, we would expect that to be paramagnetic, and it's not. Okay, so we'll look at that in a second, of how we would determine whether this level was above or below. So at this point, you're really just going to have to know that it's lithium through nitrogen, that this level is above the pi bonds, and all the other molecules it's below. And we'll see a comprehensive chart here in a couple of slides. So, oh no, it's the next one. Here we go. So this is that level. So if we look at those levels, we have the A1 GU, the E1U, and the A1G is this one here. That's that PZ sigma bond. And that's where it is in lithium. So dilithium. What? Dilithium? Yeah, that's a real thing. It's not a crystal and it won't help your warp drive, but it's a real thing. Okay, not too many people watch Star Trek anymore, but so anyway, sorry. So then you follow that, and you see the sp mixing gets smaller and smaller and smaller as we get to larger and larger atoms. So when we get to nitrogen, it's still present, but when we get to oxygen and fluorine, it's pretty well gone away. And so then this A1G level has now gone below the pi bonding levels. Everything else is the same. And so again, this symmetry tracking, these labels here, it's nice to use sigma and pi's, but when we get to bigger molecules, we're going to have to resort to just the character table labeling, the Millikan symmetries. And so I've put them in on the diatomics so that you don't get too attached to sigmas and pi's. Sigmas and pi's are great for diatomics. When you get to benzene or ammonia or whatever, then it kind of starts to fall down in terms of the molecular orbitals. But let's look at this. Experiment confirms that boron and oxygen are paramagnetic. What's paramagnetic? Well, if you put this electron cloud in a magnet and you have unpaired spins, you can detect those unpaired spins. If they're paired up, they're diamagnetic. So you can actually separate oxygen gas, liquid oxygen, from other liquid, like liquid air. So you could pour a liquid air through a magnet and the oxygen would get stuck. And it's not because it's ferromagnetic, it's not the nuclear spins that we're taking advantage of, it's the electron cloud spin, it's paramagnetic. So we can use magnetic properties to determine something about MO diagrams. And so that's how we know about this sp mixing business, because if this level were down below, then boron would be diamagnetic, right? Those 2 electrons would go into that sigma bond and they would pair up and you wouldn't have any unpaired spins. But because of sp mixing, this level is above, and those next 2 electrons go into these degenerate p or pi bonds, and so then they're unpaired and it's paramagnetic. And we can do the same thing with the anions and cations to test these other levels. So practice this calculation. For all of these on this table, you should understand these bond orders. So the number of bonding electrons, and you subtract the number of antibonding electrons. So I put the little stars on here to show these are the antibonding levels. And so if you take the bonding, so let's do this for fluorine again. So 2, 4, 6, 8. And let me do it on the pen. So 2 here, 4, 6, 8, minus 2, 4, 6. So we have a net 2 electrons. Divide by 2, that gives us a single bond. And so here are your bond orders for all of the second row diatomics. I don't have the neon on there because it would be a bond order of 0, but that would finish out the second row with neon having a bond order of 0. Okay, this is the exciting part. I've talked to you about molecular orbital theory this whole time, and the bond orders are what are predicted, one of the things that's predicted by MO theory. And so this would be the bond order for those second row and the cations. So here's H2, and if you take 1 electron away, it should have a bond order of 1/2. Here's He2, so helium. If you take one electron away, you just have one in the antibonding, so it ought to have a bond order of a half. Makes sense? Lithium, dilithium, bond order of 1. Beryllium, that 2s orbital is full, so when you bring it together, you got bonding and antibonding, so diberyllium should not exist. Boron, carbon, nitrogen. If you make nitrogen cation, it drops in bond order. If you make oxygen cation, it gets stronger. So oxygen cation has a 2.5 bond order. Nitrogen cation has a 2.5. Fluorine and neon. And what's neat about this is the data for bond energy. So a stronger bond order should give you a stronger bond energy, and look at that same pattern. Isn't that fantastic? Yeah, that's cool. And so then if it's a stronger bond, it ought to have a smaller bond length. And so the next one's bond length. And so the strongest bond has the smallest or shortest bond. The strongest bond is the shortest. Higher bond order, shorter bond length. It's not as sharp down here at the bottom.
Kind of inverse.
Yeah. So it's an inverse relationship. Here at helium is a bond order of 0, and yet you can see in nature some dihelium, but look how long that bond length is. That's not a covalent bond. They're just stuck to each other. That's what we call a van der Waals interaction. And so they're small enough that it's 300 picometers or about 3 angstroms, and so that's what you've got. And then this last one is force constant, so the vibrational force constant. So there's a lot of things that confirm the structures that we get from molecular orbital theory. And then one more sort of nail in the coffin for local bond theory is the Lewis dot structure for carbon, dicarbon, should predict a quadruple bond, right? Octet rule, you got 4 electrons apiece, a quadruple bond for carbon, and it's not. Okay, it's got a bond order of 2. Okay, so we've got probably not enough time for the Kahoot, but that's okay. I want you to review the notes. And then next time at the beginning of class, we'll do like a 10-question Kahoot on all of this and see if you've really stuck it in your head. All right? So.